go on to introducing the notion of probability. How many 11-letter strings are possible if there are no repetitions? I mean, if there's no restrictions on repetitions, how many 11-letter strings are possible? You can have 11 in the first spot. You can have 11 in the second spot. You can, right? No, sorry. There are 26 letters, and there are 11 slots, and you're allowed to repeat the letters. Yes? Yeah, so, right. So there are 26 letters, and you can put each of those 26 letters in the 11 spots in the 11-letter string. So the answer is 26 to the 11. Okay, so here we have, say, 11 letters. And we're going to make rearrangements of these. How many distinct strings can we have? How many permutations of 11 distinct symbols are there? 11 factorial. There are 10 different people. They all want to serve on a committee. The committee consists of 3 people, and those are not distinguished in any way. Okay? So we can think of this as there are 10 symbols, and they need to be partitioned into 2 piles. One pile has the 3 people that we've selected, and the other has the people we've rejected, right? And there's no ordering within the piles. Okay? So based on what we did last time, how many ways? Okay, you can think of it this way. You have 1, 2, 3, 4, 5, and so up to 10 slots. Right? So how many ways are there of arranging 10 symbols? How many rearrangements of 10 symbols are there? Distinct symbols. There are 10 factorial ways to arrange those. Okay? But if we make a distinction now, this is the top drawer in which we have the selected people, and we have a bottom drawer in which we have the unselected people, right? So the rearrangements in here don't matter to us. They're all members of the committee, and we don't distinguish them in any way. So rearrangements within the top drawer don't matter. So there are 3 symbols here. So a factor of 3 factorial from here is contributed to this 10 factorial. That's an overcounting. So we need to divide by that. Over here we have 7. 10 minus 3 is 7. So there's an overcounting of 7 factorial in this 10 factorial. So it's 7 factorial. And this is also, we're using this notation, right? We read that notation as 10 choose 3. Okay. Any questions about that one? Right? How many ways are there to choose 3 distinct objects from 10 distinct objects? And then the ordering of the choice doesn't matter. 10 choose 3. Okay, let's make it a little bit different. There are 10 people who want to be chosen, and when we choose them, one will be the chair of the committee, one will be the secretary, the other will be the ordinary member. So now the ordering within that pile, those orderings are different, right? But when we look at the pile of rejects, we can write that list in any way that we want. and you still end up with the same committee, right? So now how many ways are there using the factorial notation? Yeah, well, let's just remove the 3 factorial, right? This ordering matters, okay, and it's contributed to the 10 factorial. The ordering in here, which also contributed to the 10 factorial, does not matter. Right, so there were 7 factorial ways of writing the list of rejected people, but you still end up with the same committee as long as you don't change this one. So in this 10 factorial, you've overcounted by 7 factorial. Okay? And that's the same as 10 times 9 times 8. Right? How many permutations of these letters are there? There are 8 distinct symbols, so 8 factorial. Okay. Yeah.
About this example, people explain how 10 to 9 to 8 is the same as 10 C7.
Yeah. Okay. We have the rule that one way of defining n factorial is to say that n factorial is n times n minus 1 factorial. So I can write this as 10 times 9 factorial. Okay, and I can also write this as 9 times 8 factorial. Right?
Sir, but this is mathematically, if you could explain it using the 10 members of the National Assembly, as in if you choose one to be...
You mean, you want... Okay. Well, let's say 4 people volunteer to be on the committee. One will be called the chair of the committee. One will be called the secretary of the committee. Right? And then there's a list of rejects. Okay? So if let's say we have Adel and we have Bilal, they get selected this way, and then we have X and Y are the rejects. Okay? Now, if I write out a list like this, there are 4 factorial ways of writing out this list. Okay? Now, if Bilal and Adel were to interchange, then I would have a different committee. Right? So there's no overcounting here. Okay? But here, if I write the list of rejects as X and Y, or I write it as Y and X, then it's the same committee and the same list of rejects. So interchanges among these are not changing the number of committees. But when I wrote 4 factorial, 2 factorial was coming from here. So because of this, I have to divide this. That contributed an overcounting of 2 factorial. But changing these does in fact change the committee. So there's no overcounting here by counting from here, the contribution from there. Okay? Okay, so what did we have? We had 8 distinct symbols. Now we ask, how many arrangements are there in which C is the 3rd letter? Right? So C is fixed. Right? So for the first one, there are 8 that you can choose from. From the second one, there's 7, well, there's only 7 you can choose from because the C is fixed, right? So we can write all the other ones. There'll be 7 factorial ways of writing that one, and there's only one way of placing the C. So that condition reduces the number of orderings to 7 factorial. How many words are there in which the word starts with a consonant? Okay, let's go back here. Okay. There are 1, 2, 3, 4, 5, 6 consonants in that. Let's count the number of, because there's fewer vowels to do. So we can count the number of vowels and then subtract, right? We can count the number that start with a vowel and then subtract. Okay? So there's 2 vowels, A and E. The number would start with A. So you've used the A. There are 7 slots left over, 7 factorial ways of arranging in those 7 slots. And then there's, for the E, same reasoning. There's 7 factorial strings which start with E. So there are 2 times 7 factorial which start with vowels. There were 8 factorial total strings, so 8 minus the ones that start with vowels are the number that start with consonants. So 8 factorial minus 2 times 7 factorial. Okay, so you can also say that out of 6 consonants, I have to pick 2 of them. So I can pick 2 of them, and then there's the rest of them. Okay? So there could be a number of ways of doing this problem. Okay? So, like I said, there's a number of examples in that file. You should go through them all, right, just to make sure that you understand these counting arguments. Okay? So for now, let's assume that we know how to count. And now we will finally introduce probability. We have an experiment. And there is a set of possible outcomes, which we call the sample space. We usually write that as S. And then there are subsets of that S. So imagine all the possible subsets of that S. And then we assign probabilities to those subsets of the sample space. And we assign probabilities between 0 and 1. The larger the number, the larger the probability, the more certain or the more likely the event is. So in particular, if I assign 1 to an event, if I assign a probability of 1 to an event, it means that that event is absolutely certain. That outcome is, right? If I assign 0 to an event, it means that that event cannot occur. We have a sample space S. It's a set. There's a subset A of the sample space. A gets assigned a probability that lies between 0 and 1. The probability of the sample space is 1. So the probability that one of the outcomes out of all the possible outcomes occurs is 1. Right? And the probability of the empty set is 0 because none of the possible outcomes are in the empty set. So let's take an example. We flip a coin. We record either H or T. Okay? So the outcomes are, well, S can be written as the set with the element H in it and the set with the element T in it, and we take the union of those 2 sets. So the probability of H union T, well, that's the same as the probability of S. So that's equal to 1. If we consider rolling a die, 6-sided die, and we consider all the possible outcomes of that, right? And then a subset of those possible outcomes is this A. Another subset is this B. So A should be assigned some probability between 0 and 1. And B should be assigned some probability between 0 and 1. Now, A is not certain. It's not absolutely certain that you would get that outcome. It's not absolutely certain that you will get a 1 or a 2 or a 3 or a 4. So this shouldn't be assigned a probability of 1, for example. But this event could occur, so it should be assigned a probability bigger than 0. Right? Okay, now, what about the intersection? Well, if we take the intersection, what do we have? We just had the intersection of event A and event B is that you roll a 4. What's the probability of rolling a 4? If we assume that the die is fair, the probability of rolling a 4 is 1 out of 6. Right? A fair die is one in which each of the outcomes is equally likely. That isn't true in every probability problem. But if we're talking about a fair die, it means each of the outcomes is equally likely. If we're talking about a fair deck of cards, it means if I draw one card, all of the probabilities are the same of drawing a particular card. Consider probabilities of unions, intersections, and so on, collections of events. And so we have some rules for dealing with that. Okay? And basically, the rule I'm going to show you is basically a way of preventing the overcounting of probabilities when you take unions. A and B are events. They're subsets of the sample space. Right? So they're shaded, right? And then you've got this intersection is white. Okay? The elements of the intersection are in A union B, are in both A and B. Okay, so supposing that you knew the probability of A, and you knew the probability of B, and you had some way of calculating the probability of the intersection. Right? Let's just suppose you know that. I want to relate the probability of A union B to all of those other probabilities. The rule is that if you want the probability of a union, A union B, that's the probability of A plus the probability of B minus the probability of the intersection. And the reason you have that is that the intersection is in A and the intersection is also in B. So if you just wrote probability of A plus probability of B, you would be counting the probability of the intersection twice. So to avoid that, we subtract off that one intersection. Okay? Once again, if A and intersection B is empty, if there's no common element that's in both A and B, then we say that A and B are mutually exclusive or disjoint. We introduced that before. In the special case of mutually exclusive events or disjoint events, the probability of A union B is the probability of A plus the probability of B minus the probability of the intersection. But the intersection is empty for disjoint events. So we get the null set. And the probability of the null set is 0. So in the special case of disjoint events, the probability of the union of A and B is just probability of A plus the probability of B. Okay, so working with mutually exclusive events is convenient. So when you're thinking about the problem, if you can think about the problem in terms of mutually exclusive events whose probabilities you can calculate, then calculating the probability of unions is simple. What if you had a whole bunch of events which were mutually exclusive? So we've been talking about two events, but the idea extends. If I have events A, B, and C, and they're all pairwise mutually exclusive. So A intersection B is empty, B intersection C is empty, and A intersection C is empty. Then when we start calculating the probabilities, the probability of the union is just the sum of the probabilities of the individual events. because there are no elements which are common to different AI here. Yeah.
इस चीज के साथ linear है left hand side पे.
All of the AI. So if I have probability, let's say A union B union C, that's the probability of A plus the probability of B plus the probability of C minus some probabilities of intersections. Okay? But the intersections are all empty. So they don't contribute to the probability, and so you're just left with this. So once again, you want to try to work with mutually exclusive events if possible, right? We'll see that more when we do total probability. We're rolling a die, and we're recording the result. Okay? So S consists of all the rolls. This is the union of rolling a 1 and rolling a 2, right? Right, so the set 1, 2 is the union of the set containing 1 only, union with the set containing 2 only. Okay? So the probability of rolling a 1 or a 2 is equal to the probability of rolling a 1 or a 2 minus the probability of the intersection, but the intersection is empty, so we don't have to think about that. The probability of rolling a 1 or a 2 or a 3 or a 4 or a 5 or a 6 is the probability of rolling a 1 plus the probability of rolling a 2 and so on, right? Because if we take the intersections of those, they're all empty. And so they contribute 0 to the probability. What about if we have 3 events and we want the probability of their union? Well, it's the probability of A plus the probability of B plus the probability of C minus the probability of the intersections of 2, all the possible intersections of 2 of the events. Okay? But when we do that subtraction, we've taken out the triple intersection too many times. So we put that triple intersection back in. Okay? So in this course, we're not going to be worrying about intersections, well, unions of 100 events or something like that. So, yes?
What if we have 3 events, 2 of which are mutually exclusive?
We have 3 events, 2 of which are mutually exclusive. So let's say, yeah, so then you'd have 2 of those terms would be 0. And if the other one was non-empty, you'd have a non-zero term, right? And probably the triple intersection would be empty. Yes?
Sir, ये sir last time we had cases.
Yeah. See, the triple intersection is in all of these, and it's also in all of these. So you included it in that top row 3 times, and then you took it out in the top row 3 times, so it's not included yet, so we put it back in. Okay? Draw the Venn diagram. You'll see. Yeah, any other questions?
Sir, उसको हमने निकाला और इसको ऑफिस डाल दिया.
Yeah, like I said, here you have events A and B. I want the probability of their union. So when I say the probability of A, now I've counted the intersection once, plus the probability of B, now I've counted the intersection twice. So I should subtract off the probability of the intersection. Okay? Now I do another one. Okay? So I have the idea that I need to subtract off the pairwise intersections. But then the triple intersection is included 3 times in the top line. Then it's taken out 3 times in the second line. So I've got to put it back in once, otherwise it'll go missing. Yes?
I'm taking it out 3 times.
Yes. In the second row, I'm taking it out 3 times, right? Yes. So I've included it 3 times. Then in the second row, I've taken it out 3 times, the triple intersection. So now the triple intersection is not included. So I put it back in once. Yes.
How do we interpret this basically? The union of probabilities means the probability of each event occurring simultaneously.
The probability of one of the outcomes within the event occurring, right? Okay. Now we need a rule for complements also. All right. So how did I get the complement of A? I took S and I ripped out everything that was in A. That's a complement of A. So I take the union of A with its complement, then that gives me all of S. Okay? So for any set, any subset of S, if I have A union with its complement in S, I get all of S. Okay? Now, what is the probability of S? We assign 1 to the probability of S, right? So the probability of A union A complement is the probability of S, which is 1. Okay? Now, what's the probability of A union A complement according to these rules we've been talking about? Probability of a union? Yeah? So, the probability of A union A complement has to be equal to 1. And it's also equal to, according to that formula, it's equal to the probability of A plus the probability of A complement minus the probability of the intersection. But the intersection of A and its complement is the null set, as you say. Okay? So that probability is 0. Okay? So that means that the probability of A is equal to 1 minus the probability of A complement. Okay? So this is a handy rule to have, because sometimes you want to calculate the probability of A, but it's not so easy. But calculating the probability of A complement for some reason is easier. So you calculate the probability of A complement first, and then 1 minus that probability gives you the probability that you originally wanted. Okay. Another set operation, we've talked about unions when we've talked about intersections and complements. We can also talk about set difference or set minus, right? So A set minus B means that you have A, you have B. This means everything that's in A but not in B. So when you have A and you remove A intersection B from A, what you have left over That's the set difference. Right? So A set minus B means this. Okay? So that means that A is equal to this plus A intersection B. All right, so if you want to write A in terms of set difference and B, you write it as A is equal to A set minus B union A intersection B. Yes.
Set difference even 3 section and the elements are unique to this.
Well, okay, so if you wrote, if you wanted to bring in another set difference, right? So let's say you'd have C is here. So you would have to also take this part out of your original set difference. Yes?
Is this not just only excluding like the triple intersection and not the AC intersection?
Well, what you would do is, if we decided that we're going to do this one first, and then we're going to subtract C from it, right? You'd say, take A, take out everything that's in A which is in B, which is the intersection. Now, if there's anything left which is also in C, take that out. Okay, so now if you calculate the probability of A, that's the probability of A minus B plus the probability of A intersection B minus the intersection, but that's empty. The probability of A is the probability of A minus the intersection with B plus the probability of the intersection. That gives you all of the probability of A. Okay, so that's one way of writing it. And now, let's suppose we were interested in the probability of A minus B. Then that's the probability of A minus the probability of the intersection of A with B. Okay, and once again, if I want the probability of A, I can take the probability of A, the unshaded part, that's A minus B, right? And then I have to add in the probability contributed by the shaded part, which is A intersection B. So the probability of A is the probability of A minus B plus the probability of A intersection B. That's what we're saying.
So what's the point of taking it out if you're just going to add it back?
Because it can make our calculations easier. Right? So if we're asked for, what's the probability of A minus B? Well, it's the probability of A minus the probability of A intersection B. Okay, so let's try a problem using these ideas. Okay. 60% of the students at a school wear neither a ring nor a necklace. 20% wear a ring, 30% wear a necklace. Okay? Okay, so we might write it like this. Okay, so there are 60% who are not wearing a ring or a necklace, right? % of the students wear a ring. 30% wear a necklace. Some might be wearing both. Okay, so that's the situation. If one of the students is chosen randomly, what's the problem that the student is wearing a ring or a necklace? And what's the probability that the student is wearing a ring and a necklace? Okay, so let's work our way through that. What's the possibility? Student could be wearing a ring. Student could be wearing a necklace. Student could be wearing neither, right? So if you're doing a problem, then make sure, name your sets or name your events, right? And tell me what the names mean, right? Don't just write a formula involving R, N, and U if you don't tell me what those events are, okay? Okay, so what were we given? 60% wear neither a ring nor a necklace. 20% wear a ring, 30% wear a necklace. Okay, so that means that the probability of the random student not wearing a ring and also not wearing a necklace is 0.6. Probability of wearing a ring is 20%. Probability of wearing a necklace is 30%. The probability of wearing a ring or a necklace, okay, let's say I tried to do that directly. I got kind of confused. And I said, okay, let's try working out the complement and we'll take 1 minus the complement. So the probability of wearing a ring or a necklace is 1 minus the probability of the complement of R union N. Okay? Well, what's R union N? That's the set of people who are not wearing a necklace and who are also not wearing a ring. Well, that's what I called U. So it's 1 minus the probability of U. Oh, but what was U? We were given that U was 60%. So the probability that the student is wearing a ring or a necklace is 40%. Okay, so that's a simple problem using our ideas. Yes?
So let's say the question asked us to calculate the probability of students who wear both.
Yeah, okay, so that's part B here, right? So yeah, so we're gonna do that. The probability of wearing a ring or a necklace is the probability of wearing a ring plus the probability of wearing a necklace minus the probability of the intersection. We had that rule, right? And that's what we're trying to find. So we found that this probability on the left was 0.4. So that's equal to probability of R was 0.2, probability of N was 0.3, minus the probability that we are trying to find. Okay? So the probability that we're trying to find is 0.1. Those were some what are called additive rules for probability. Okay, you're going to need these throughout the course. Now, there are some particular cases that are of importance. You have to be careful. We're going to discuss the case of when all the outcomes are equally likely. That's not always true. Okay? You shouldn't assume that it's true unless it's obvious or it's been given. Okay? But now we can look at the case of equally likely outcomes. Okay? So a fair die, every possible result of the roll is equally likely. A fair deck, nobody's cheating. Each card is equally likely to be drawn from a well-shuffled deck. Okay? So those are the sort of things that we're talking about. So let's say that there are n distinct outcomes. I have an experiment. It has n distinct outcomes in the sample space. Okay, so maybe we'll call them AI up to AN. And then they're equally likely. So capital AI is the subset of S, which contains only small ai. Okay? So each of these, the probability of each of these AIs is equally likely, so let's call that P. Okay? So the probability of the sample space is 1. These are all this is the list of equally likely outcomes. Now, I can separate them out individually, like this, because this is the union of, S is the union of capital A1, union capital A2, union up to capital AN. Okay? And then I'm going to subtract off the intersections, but these are different distinct outcomes that we're talking about. So the intersections are empty, right? Okay, so no problem. I just need to add up the probability of each of the individual outcomes. Okay, but each of the individual outcomes is equally likely. So I have 1 is equal to P plus P plus P and so on, n times. So 1 is equal to NP. When we have equally likely outcomes, and there are n, capital N outcomes, the probability for each of the equally likely outcomes is 1 over n. So I have a fair coin and I flip it. There are 2 possible outcomes. That means that the probability of either H or T is 1/2. I have a fair 6-sided die. There are 6 outcomes. They're equally likely. So the probability of each outcome is 1 over 6. If you have n possible outcomes, they're all equally likely. The probability is 1 over n. Yes?
So for this to be true, would the events have to be independent of each other?
Yeah, I think so. Yeah. It's are the events. Well, we'll get to independence of events later, so I'll talk about that then. Okay. Now, what if we had something like, what's the probability of B? B is some subset consisting of a certain number of equally likely outcomes. Okay? So, B consists of small n of the capital N equally likely outcomes. Okay? So what's the probability of B? Well, the probability of B is the probability of this set plus the probability of that set, and so on up to the probability of that set, minus the probability of the intersections, which is empty. And we know what the probability of each one of those is. It's 1 over capital N. Yes?
Can unions be interpreted as sums of probabilities?
Unions? Unions should be considered to be, in a sense, the sums of possible outcomes, not the sums of probability. Well, there were small n of these. Each one had a probability P, but P was equal to, well, so NP. Okay, but what was P? P was 1 over capital N, the total number of outcomes in the sample space. So, when you have finitely, yes?
Can you revisit वो n over p वाला part?
This one?
Yes, this one.
Yeah. So I had a subset of the sample space which had small n elements in it. Okay? Then I break it up as a union, like when I'm calculating its probability. Remember, the intersections are empty, so I can leave that part out of the formula. And so you have small n of these. Each one has p. So you get np, but p was equal to 1 over capital N. Okay? All right, so one way of writing this is that I have a sample space S, right? It has a certain number of outcomes, capital N we called it. I have a subset of S called B. So what's the probability of B? The probability of B is the number of outcomes in B, the cardinality of B, divided by the number of outcomes in S, which we call the cardinality of S. How many 4-card hands are possible, right? You have 52 distinct symbols in a fair standard deck, and you have to choose 4 of them, right? You have to divide them into a pile. Here's 4, which we've accepted. Here's 48, which we've rejected. And internally, within the piles, ordering doesn't matter. So the number of 4-card hands that are possible, 52 choose 4, by the rules we've been talking about. And it's a fair deck. Fair deck means all of the 52 choose 4-card hands are equally likely. Nobody's cheating, right? All right. So what's the probability of being dealt a particular 4-card hand? What's the probability of an outcome of having exactly the hand that has an ace of clubs, ace of spades, queen of clubs, and queen of spades? Okay? That's one outcome out of the 52 choose 4 equally likely outcomes. So by our rule, 1 divided by 52 choose 4. Okay? 1 divided by 52 choose 4. The general rule is when you have equally likely outcomes, finitely many outcomes, the probability of B is the number of outcomes in B divided by the number of outcomes in your sample space. Okay. B is the event of getting exactly that one particular hand dealt to you. So there's only one element in B. All the possible outcomes are 52 choose 4-card hands, right? We have to divide 52 symbols into a pile of 4 and a pile of 48 without ordering in between. So those are this thing that we write like this, right? Which is 52 factorial divided by 4 factorial divided by 48 factorial. Okay? So 1 out of 52 choose 4. 1 divided by 52 choose 4. Okay. What is the probability of being fairly dealt the 4-card hand which consists exactly of the 4 queens? Same thing. It's one particular hand out of 52 choose 4 hands. All hands are equally likely. What is the probability of being dealt either one particular hand or a second particular hand? Right. This time you've got 2. The number of desired outcomes is 2. The set of desired outcomes is 2 out of 52 choose 4. 2 out of 52 choose 4. Yes?
When you say choose, you're saying combination, right?
Well, I'm saying partitioning into 2. By choose, I mean partitioning into 2 sets.
52 choose 4.
Yeah, 52 choose 4 means I had 52 symbols. I set 4 into one pile, which I called a hand. I have 48 symbols that I didn't put in my hand, right? And the orderings in my hand or the ordering in the reject pile are not important. So I call that 52 choose 4, which is also this.
Isn't that the same as 52 combination? So there's both are.
Yeah, okay, yeah. So some people write that as 52C4, if that's what you're thinking. Yeah. Yeah.
Instead of the question having like 2 sets which had like different cards each, there were 4 queens in one
Yeah.
hand, like absolutely different cards in the other hand. What if the other hand like had a card, like had a queen as well? So
Okay. Yeah. Okay, but those would be distinct hands, so it'd still be, no?
They would be distinct hands, but they would have. So if I got one, then it would be impossible for me to get them.
Yeah, yes. Yeah, well, we're hoping for that, yes. Yeah, so the same rule applies.
The answer would be the same.
Yeah. Yeah, if you say, what is the possibility of this kind of a hand? Well, you look at all the outcomes that give you that outcome. So you look at all the outcomes that meet your condition, and those number of hands which meet that condition divided by 52 choose 4 is what you want. Yes?
What if the question was, what's the probability of choosing no particular 4-card hands?
Okay, so if there are two, if the event that you're looking at has 2 elements in it, then it's 2 divided by 52 choose 4 is the answer.
But what if अगर हमने वो जो hands हैं वो उसी deck में से choose करने हो? Like we have to.
No, I wasn't saying you have some condition on the number of desired hands. I want all the hands that meet this condition. So you count up all the hands that meet that condition, and then you divide by 52, choose 4. So here's an illustration. You have a 4-card hand. You have the ace of clubs. You have the ace of spades. You have the queen of clubs. And I want any of the heart cards. Okay, so let's not worry about probabilities right now. B is the event that you got any of the hands which meet this condition. So how many ways are there of constructing this hand? First, we have to look through the deck, and we have to select the ace of clubs. There's one way of doing that. Then we have to look through, and we have to select the ace of spades. One way of doing that. Then we have to select the queen of clubs. There's one way of doing that. How many ways are there to choose one of the heart cards? Okay? 13. Out of 13 heart cards, I have to choose one. So 13, choose one. So there are this many cards, 4-card hands, which meet my condition. Okay? All hands are equally likely. What's the total number of hands? 52, choose 4. choose 4 equally likely hands. So 1 over that times the number of hands that meet the condition that you've set. Okay. You're dealt 4 cards from a 52-card deck. So each deck has 4 aces and 4 kings, right? What's the chance of receiving 2 aces and 1 king? All right, so how many ways are there of constructing this hand? Let's use our rule of counting. So first we have to receive 2 aces. So out of 4 aces, we have to choose 2 of them. Okay? Now we're going to have, there are 4 kings, and we need to choose 1 of them. Now, I need two more cards. So how many cards are left over to choose 2 from? No. I can't choose another ace. I can't choose another king. Let's say we want precisely 2 aces, and we want exactly 1 king. So I'm not allowed to choose any, right? So there are 44 left, 44 cards left that I'm allowed to choose from. And I have to choose, I've chosen 1, 2, 3 cards, so I have to choose one, right? There are this many 4-card hands which meet my condition. All hands are equally likely. Yeah?
44 or 48.
Oh, right, 44. Sorry. Right, because we've excluded, there are 8 cards now that we can't choose from. Right? So, okay, so those are the total number of hands which meet the imposed condition. Right? Now we divide by the number of hands because all hands are equally likely. Yes?
In the previous example, why did you not do 4 choose 1 and instead you choose 1 into 1 into 30? You had to.
Oh, okay. We want to construct a 4-card hand, and it's to have 2 aces and 1 king. Exactly 2 aces and 1 king, right? So we think of it as a 3-step process. Use our rule for counting, right? So 4 aces, choose 2 of them. 4 kings, choose 1 of them. There are 44 cards left which are not kings and which are not aces. Out of those, you have to choose 1 of them. So this is the total number of ways of constructing a hand which meets our required conditions. And then every one of those hands, every 4-card hand is equally likely. So how many are there? There are 52 choose 4 4-card hands. So we divide by 52 choose 4. Try this one. You have a 20-sided fair die. What's the probability of getting an even number? 1/2. Okay. All right. So, any questions? No? All right. I'll see you next week.